Section 7.6 is where we start to talk about the shapes that the electrons occupy as they surround the atom. And now keep in mind, because of Heisenberg's uncertainty principle, that these are probabilities of electrons being within a certain dense location of space. So if we look at the 1s orbital, which I told you before has kind of a spherical orbital shape, we can see the little dots as indications or solutions of the wave equation that give likelihood of finding an electron somewhere from the nucleus right here at the center and some distance away from that nucleus in three-dimensional space. Now we can look at this as kind of a one-dimensional curve of how likely we are to find the electron at a certain distance from the center, and you can see the highest probability is actually at the center of the atom, or at the nucleus. Now, the volume of space occupied by the very center of the atom is infinitesimally small. As we get farther and farther away, we're looking at volumes that get larger and larger and larger. So if we actually look at this as a function of the radial distribution, this density, the chance of finding something at a particular distance, combined with the increasing volume as the distance gets farther away, actually gives us kind of a maximum chance of finding an electron within a certain volume from the center of the nucleus outward to be, for hydrogen at least, about 52.9 picometers. Okay? So the electron in this 1s shell is most likely located right here. I mean, it still has a chance to be located within a certain plus-minus distance of that, and you can see that we actually go to very little likelihood of finding it right at the nucleus, because that has such a small volume that even if we have a high probability times a very small volume gives a very low overall probable density. And the kind of sweet spot for all of this falls right here. Okay? So the upshot of this, the kind of take-home message, is the 1s orbital and all of these orbitals have some sort of probability and likelihood of finding an electron, which you then multiply by the volume of space occupied by that particular probability to get this second function, which is the likelihood of finding an electron at a given distance. So if you take this likelihood and distance radius and you put it into three-dimensional space, we get a sphere with a certain thickness. And that represents the shape of the 1s electron. Let that sink in for a second. This is the shape that we talk about when we talk about a 1s electron. This overall occupation or space that this shape occupies is what we think of when we think of the 1s electron. Now for 2s and 3s, just like waves can have nodes, you can kind of think of this easier with a standing wave. If we have something oscillating back and forth through space, oh, that should overlap there. We have kind of this space where right here, right here, right here, we get zero amplitude. And we represent these as nodes in space, and nodes on a probability distribution, density function graph like this, represent 0% chance or probability of the electron occupying that space. So this node right here for the 2s orbital and these two nodes for the 3s orbital correspond to zero likelihood of finding an electron in that distance. So we have the same kind of probability density function that we saw before, where we have a very high probability right at the center, and we have a lower probability but larger volume as we go farther out. multiplying the two together, give us this small likelihood of finding it closer in, like the first s electron was, the 1s electrons are, and then a much greater likelihood of finding this electron at this distance somewhere here around 300 picometers. Okay, so this whole set, it represents the same orbital, the same electron. So there's kind of this little area in the middle and a much bigger and more likely area overall because of the volume it occupies farther out. The 3s has two nodes. Okay. So we have likelihood, zero likelihood, likelihood, zero likelihood, and finally highest likelihood right through here of where the electron is going to be. Now if we get into P-shaped orbitals, we have a different distribution. We actually have these kind of lobes, and both lobes are the same orbital, but now the solution to that function that gives us a radial distribution, and we just kind of look at this along the lobes. So we're just kind of starting here at the nucleus, starting here at the nucleus, and then going outward through the lobe. We see we have basically zero probability of finding it near the nucleus. It increases and then kind of tapers off as we get farther away. So the electron in these lobes is occupying a space that has no probability close in, where the s orbital is. And instead, we have probability farther out. Now that doesn't mean that the s orbital doesn't occupy this kind of space, and we'll get into what these look like combined later, but just kind of for now, keep in mind that the s orbital takes up two lobes for one, the p orbital takes up two lobes for one electron's orbital. So this is one p orbital. And now remember, this is 2, talking about n equal to 2. P, so L equals to 1. And now we have 3 orientations in space. M sub L can equal -1, 0, and 1. So this particular one we can designate as -1, and this one is 0, and this one is +1. Don't memorize whether x, y, or z corresponds to -1, 0, or +1. We're in 3-dimensional space for objects that are spinning around and tumbling around in the air. X, y, and z don't have a whole lot of meaning here. Just keep in mind we have different orientations they can point. The farther you get in terms of the shape number, and this is L equals 2, or D-shaped orbitals, now we start getting to these clover leaves where you have 4 lobes with 2 nodes in between them, and these lobes all represent one possible D orbital. Okay, so there are 5 different versions of this, 4 that look pretty much like clover leaves, and a 5th one that looks like a p orbital, except it's got a donut around the center of it. There is a node here, and there's actually a node that goes between the center and the donut as well. So there's still 2 nodes for each of these different orbitals. By the time we get into F-shaped orbitals, things have gotten extremely complicated. We have all sorts of different designs and clover leaves and toruses and things in different shapes. You don't have to memorize any of these shapes, certainly. S and P you should be somewhat familiar with. D you should be able to recognize. But F, don't bother memorizing these shapes. This is just for illustrative purposes. All these different possibilities. We have all of these different M sub L orientations in space. -2, -1, 0, actually -3, -2, -1, 0, 1, 2, and +3. So we have all of these different ones. Which one corresponds to which M sub L? Again, don't worry about it. This is 3-dimensional space. It's not going to be that big of an issue for this class. Just know that there are all of these different orientations in space for an F-shaped orbital altogether. There's one last aspect of this that we have to know when we get to overall shapes of these different molecules, and that is that these waves, just like a one-dimensional wave, can have a phase. It can have a positive character phase and a negative character phase. And s orbitals actually only have positive character phase, while p orbitals and beyond can have positive and negative character phase. So what does this kind of look like when we draw them in three-dimensional shapes? We usually give the different phases colors. So the positive, we're going to give blue, while the negative phase, we're going to give red. Now, this is still one electron occupying this space, node in the center, between the positive and the negative phase solution for this particular set of orbitals. Focus on the shape, focus on correlating the S, P, and D, and F to shape, and that is the main thing that you want to take home from this particular section at the end of the chapter. So the overall idea, well, we have all these different crazy shapes for the orbitals. Why do we represent atoms as spherical? Well, we represent them as spherical because if you put all of these different orbitals together superimposed, like an atom will have, basically you get a shape, an overall surface that's going to be a sphere. We'll get into other shapes, such as shapes of molecules, in subsequent chapters, right about chapter 10, actually.